Well, hi everyone, and greetings from Northern Michigan. This is Bob the Science Guy. You know, I've been spending an awful lot of time looking into the psychology of flat Earth and other science-denying communities lately, but I am the science guy, so I thought it would be a good time to start a new series on some actual science. Today I'm going to start that series on the atmosphere, refraction, and miraging, and I'm going to be relying heavily on the work of Dr. A.T. Young, who is the guru of refraction and the darling of the flat Earth. They love to misquote him and cherry pick his work to try and deal with their ideas. Now, originally I had planned to do this as a collaboration with Dr. Young, and I contacted him. When I described what I wanted to do and how I wanted to use it to counter some of the misinformation coming out of the flat Earth, he had a couple of words of advice for me. The first was that the idea that the Earth was flat was probably the silliest thing he had ever heard of, and he didn't really feel as though he should waste his time with it. Well, I made a good case for the fact that the flat Earth brings up some very interesting misconceptions about the atmosphere and refraction, and it would be a great time to clear those misconceptions up. I told him that basically it was my hobby as a science educator to look at science denial and try and correct some of the misconceptions. And his response to me was actually quite concise, and that was, Bob, you've got a lot to offer, get a better hobby. Well, this is going to be one time that I'm going to disagree with Dr. Young. I'm going to go ahead, with his permission, and go through some of his work and clear up these misconceptions on my own. So let's buckle up, go back to the desk, grab our fountain pen, and do some science. The first thing that we need to talk about is the horizon. Now, there are a number of terms that are used for the horizon. Let's go through them real quick and see what they are. First of all, imagine that you're up on a mountaintop. Now, if you look out, everything that you see is either going to be above you or it's going to be below you. We have something called an astronomical horizon, which divides the sky into everything that is above you and everything that is below you. And it is parallel to a tangent line on the Earth at the base of the mountain. Most of us refer to this as the horizontal, and it is perpendicular to the vertical, which is the extension of the radius of the Earth. Now we have another horizon that is called the geometric horizon, and that is a line going from your position to your horizon on the Earth that forms a right angle between the radius of the Earth and the line connecting you and the horizon. So we have a right triangle right here because this is a right angle. Now we have a couple of other interesting things on this diagram. If you look at the astronomical horizon, or the horizontal as I like to call it, and the line to the geometric horizon, you have an angle right here. And that is called the dip angle. Now that dip angle in this diagram includes two factors. The first is your height above the surface of the Earth, and the second is the curve of the Earth coming down to the horizon. There's a couple of interesting things about this diagram. First of all, the dip angle is just that. It's an angle. Let's call it angle alpha. Now we know that a triangle consists of 180 degrees of internal angles. Well, this is 90 degrees right here. So we have 90 degrees between this angle and that angle. We also have 90 degrees right here. That is a right angle because these lines are perpendicular to each other. So this entire angle is 90 degrees, and it consists of this angle plus that angle. And as a result of that, and since on the triangle, we need 90 degrees between this angle and that angle, that means that angle alpha is angle alpha here. Now, it's very important to note that in this situation, we are not taking into account any refraction through the atmosphere. But in this situation, whatever this dip angle is the same angle formed here at the center of the Earth. And that's generally given in minutes of angle for things that we can see from mountaintops. Now, a minute of angle on the surface of the Earth is 1 nautical mile. So, by measuring what your dip angle is, you can tell the number of nautical miles to your horizon. So if your dip angle is 10 arc minutes, it is 10 nautical miles to your horizon. Now, the reason that this doesn't work in real life is that the Earth is surrounded by a spherical atmosphere. Now, because the Earth has an atmosphere that is curved, just like the surface of the Earth, we have to deal with something called refraction. And that brings about a second type of horizon, and that is called the refracted or the apparent horizon. Now, in the Earth's atmosphere, light rays bend downward. And as a result, we are going to get a curved line very much like that over the surface of the Earth. And this point right here is going to be something called the apparent horizon. Notice that the apparent horizon is further away from us than the geometric horizon is. Now what we have to talk about is how light is refracted in the atmosphere. How do we know that light bends down in the atmosphere as opposed to bending up? Let's go ahead and have a look at the factors involved in determining refraction in the atmosphere. Now, the first thing that we have to do is we have to understand how the atmosphere works. First of all, if this is the surface of the Earth, as our altitude increases, the pressure of the atmosphere decreases at a very steady rate. The temperature also decreases at a very steady rate. Now, refraction varies with temperature and pressure, and the relationship between those two is that refraction is related to pressure over temperature. Now, there's a couple of things that we can take home from this. First of all, if we increase the pressure, we increase the density of the air because we're packing more air into the same space. As a result, the density goes up. Likewise, if we heat the air up, we cause the air to expand. Now, as that air expands when we heat it up, we decrease the amount of matter or mass that's in that air per unit volume. We decrease the density. Now, there's an interesting observation that we can make understanding this relationship. So, as we go up in altitude, the pressure decreases. However, I think that you would understand that if we decrease the temperature by a certain amount as we increased altitude, we could get to the point that our refraction would not change at all. So in other words, if we looked straight out from our mountaintop along the astronomical horizon or the horizontal, which is perpendicular to the radius line at our feet, we could change the temperature to counter the changing pressure. So at the altitude of the mountaintop, we would have a certain pressure. As we came out here to the top of the atmosphere, we would have a lower pressure. However, if we proportionately decrease the temperature, we could set up a situation where there is no refraction occurring. Well, what would that temperature decrease be? Let's talk about the temperature lapse rate of the atmosphere. Now, what exactly is atmospheric pressure? Atmospheric pressure is the mass of the atmosphere times the acceleration of gravity pulling it back towards the Earth. Because as you know, a gas will disperse in all directions evenly unless there is an external force acting upon it. So, in order to have an atmosphere over the surface of the Earth, we have to have something that is countering the tendency of the gas to diffuse out into the vacuum of space. That is a force acting downward called gravity. The weight of that gas is the mass of the gas times the acceleration of gravity. So how do we determine the weight of the atmosphere? Well, we just look it up. Atmospheric pressure, as you know, is approximately 14.6 pounds per square inch. If you do that in metric, you come up with 10,332 kilograms per square meter. That is the weight of the atmosphere pressing on every square meter of the Earth at sea level. Now, this gives us a very interesting way to be able to work with the atmosphere. And it comes in handy in a couple of the calculations that we're going to do. assuming that the air above the surface of the Earth was of uniform density, how high would the atmosphere be? And that is a very simple thing to do. So we have 10,332 kilograms per meter squared. So how much mass is there in a cubic meter of air? Let's go look that up. So at sea level, air has a mass of approximately 1.276 kilograms per cubic meter. Now the question becomes, how high would that column of air have to be in order to weigh 10,332 kilograms? Let's just do the math. Well, when you do the math, you find that it's just over 8,000 meters high. That 8,000 meters is a very important number, and we're going to see why that is. Now remember this relationship. Refraction is related to pressure over temperature. Now the units on this are not really all that significant because it's a proportion. Now what we do with this information is we come up with something called a lapse rate. For every X number of meters, the temperature of the atmosphere drops X number of degrees. And the system that we use is Kelvin, which is related to Celsius. Absolute zero in Kelvin is negative 273.15 degrees. We're going to round it off to negative 273. So the freezing point of water, or a cold winter day here in Michigan, is 0 degrees centigrade, which means that it's 273 degrees Kelvin. Now on a hot summer day when it's 27 degrees centigrade, it's 300 degrees Kelvin here in Michigan. So let's go ahead and calculate the lapse rate that would be required for no refraction through the atmosphere. The formula is the temperature in Kelvin divided by 8,000. So this is temperature in Kelvin, and that's 8,000 meters. And that's where we use the 8,000 meters that we arrived at just a moment ago. So I've done a little bit of math here and looked at conditions that we see actually on Earth. In Michigan, the winter is 0 degrees Celsius, and in the summer, it's about 27 degrees Celsius. That's a pretty good range for our climate. Now, the coldest temperature ever recorded on Earth was negative 88 degrees in Antarctica, and the hottest temperature that was ever recorded was 54 degrees Celsius. I've gone ahead and translated these to degrees Kelvin, and then I've calculated the lapse rate that would be required for zero refraction. So, for example, in Antarctica, it would be 185 divided by 8,000. In the winter, 273. The summer, 300 divided by 8,000. And at the hottest recorded temperature on Earth, it would be 327 over 8,000. And this gives us a lapse rate in degrees Kelvin per meter. Now, what's a little bit more useful is to do that in degrees Kelvin per kilometer. So what you would do is bring over the decimal place by 3, and let's put that down. So at the coldest temperature ever recorded on Earth, for every 1 kilometer we went up in the atmosphere, the temperature would have to drop 23 degrees Celsius. At the hottest point, it would have to drop 41 degrees Celsius. And at standard temperatures, that would be 34, and during the summer, it would be 37. What that means is that to look at the astronomical horizon with no refraction, the temperature would have to drop at least 24 degrees Celsius for every kilometer we went up into the atmosphere. And that's in the middle of Antarctica at a record-breaking low temperature. At standard temperature and pressure, which means 0 degrees Celsius, that temperature lapse would have to be 34 degrees for every kilometer we went up in the atmosphere. So let's mark this zero refraction state as an atmospheric lapse rate of 34 degrees per kilometer. The temperature lapse rate is greater than 34 degrees. In other words, it's getting, it's dropping by more than 34 degrees for every kilometer we go up. Refraction would cause light to bend upward. If the lapse rate is less than 34 degrees, refraction would cause the light ray to bend downwards. Now there's another extreme situation that we can look at as well. We just discussed what it would take to have zero refraction from our mountaintop observation. And any temperature outside of that range would either cause the light to refract up or the light to refract down. Well, there's an interesting situation when we look at light refracting downward, and that is, could we come up with a lapse rate that would allow the light to curve around the Earth at the same radius as the curve of the surface of the Earth? In other words, we would look out from our mountaintop, the light would curve all the way around the Earth, and we'd look at the back of our own head. Well, turns out you can calculate a lapse rate that would allow that to happen. Now, our lapse rate to get no refraction was the temperature in Kelvin over 8,000 meters. And that gave us a lapse rate of 34 degrees Kelvin per kilometer. That's for no refraction. What about so much refraction that the light just curves around the Earth like a fiber optic tube? Well, as it turns out, the formula for that is 3 times the temperature in Kelvin over 8,000. And we change the sign. By changing the sign, what that means is that instead of the atmosphere getting colder as we increased in altitude, it would have to warm up. So let's go ahead and calculate that for 0 degrees centigrade. And the answer that we get is 102 degrees Celsius per kilometer. In other words, the air would have to warm up by more than the boiling point of water for every kilometer that we went up in order for us to be able to look out of a mountaintop and see the back of our own head. Obviously, the real lapse rate of the atmosphere is known, and it falls somewhere between these two. Well, what is the real lapse rate of the atmosphere? The actual lapse rate of the atmosphere is 6.5 degrees Celsius per kilometer. Now, obviously, 6.5 degrees Celsius is less than 34 degrees Celsius. And as a result of that, we know for a fact that light must bend down in our atmosphere. Because even at the coldest temperature recorded on Earth, you would need a lapse rate of at least 23 degrees Celsius per kilometer. Even taking a range of lapse rates to account for various factors, we cannot justify a lapse rate outside of the range of about 5 to 10 degrees per kilometer. Not 23, not 34, not 37, and certainly not 41 degrees. So we have just conclusively demonstrated that light is refracted downwards in the atmosphere of the Earth under all the conditions that naturally occur on Earth. Now, how do we calculate refraction in real life? The formula is actually quite simple. You take the lapse rate required to have no refraction on Earth in our atmosphere. You subtract that from the actual measured lapse rate of the Earth, and you divide it by the range of the lapse rate between 0 refraction and refraction equal to the radius of the Earth. So at 0 degrees Celsius under standard temperature and pressure, we'd get 34 degrees minus 6.5 degrees divided by 136 degrees. And that comes out to 0.2022. Now, that is the refraction index that I just roughly calculated right now. There are other factors involved, but again, this is just kind of a back-of-the-envelope calculation. Dr. Young uses a refraction rate of 0.179, and Walter Bislin uses a refraction rate of 0.170. Now, what kind of difference would this make if we put these different numbers into Walter Bislin's Advanced Earth Curve Calculator, where we can vary the amount of refraction? Let's go ahead and have a look. Now let's take an actual observation. This is Norwicki's famous shot of the skyline of Chicago from Warren Dunes, Michigan, 53 miles away. As you can tell, you can clearly see, for example, the Willis Tower right here. Now the Willis Tower is 1,450 feet tall. Now, my apologies for reverting to imperial measurements, but hey, America. The Willis Tower is 1,450 feet high, and the observation height from the top of Warren Dunes is 180 feet. Let's put these numbers into Walter Bislin's Advanced Earth Curve Calculator. Now, as you can clearly see, we have our observation height of 180 feet. The distance across Lake Michigan at that point to Chicago is 53 miles. The target size is 1,450 feet. Notice that I have put in 0 refraction. Now, according to that, we should be able to see the top 558 feet of the Willis Tower. So the fact that we can see the top of the Willis Tower from Warren Dunes is really no big deal. The reason that this photograph made the news was that we had exceptional refraction that day. But let's just kind of look at normal refraction. Now, as you recall, when I did my back of the envelope refraction calculation, I came out with a refraction index of 0.2022. And then I mentioned that Dr. Young uses 0.179, Walter Bislin uses 0.170, and actually surveyors typically use 0.130. However, let's just go ahead and have a look at my calculation and Walter Bislin's calculation and see what kind of error that would make in this observation. So the first thing that we're going to do is, instead of using 0 refraction, we're going to use 0.2022. And we're going to recalculate. Now, as you can see right here, 0.2022 is listed as medium refraction under Bislin's advanced Earth curve calculator. It's nothing really special. But let's see how much of a difference it makes. According to my refractive index, I should see 812 feet of the top of the Willis Tower. Now, let's go down to Walter Bislin's refraction. We'll just hit standard. And as you can see, he's got 0.1699. So we'll call it 0.17. Now, according to his calculation, we should see 773 feet of the top of the Willis Tower. Now, that makes a difference of about 39 feet from 53 miles. I don't think that that's really that much. Now, one other thing that's kind of important to look at is, let's look at the dip angle to the horizon using Walter Bislin's numbers. As you can see there, it's 0.21. So let's go 0.2166 degrees. So it's not really all that much. Let's go back to mine and see what my dip to the horizon would be. Again, 813 feet, we'll call it, visible. My dip to the horizon is 0.2123. So we're talking about 40,000th of a degree. That's really not that much of a difference in the dip angle to the horizon. So that's all I have for you guys today. In our next episode, we're going to talk about situations where we just have abnormal refraction, but no miraging. These are called looming and sinking, towering and squatting. So until then, this is Bob the Science Guy signing out from Northern Michigan. Thank you for bearing with me through all this math and science. I hope you found it useful. So the next time a flat earther asks you, how do you know that refraction curves light down? Just tell them, because I don't think the atmosphere has been set on fire recently. Take care, guys.
Mama, please make them hear me, or I can't teach them anymore. This rabbit hole's too deep for me. Feel my brain getting real sore. Bob the Science Guy. Bob the Science Guy.